So we're getting into 5.3 sum and difference identities. So on our super fun sheet, these are actually split up into 6 different identities, but the book presents them this way. I know you guys have seen plus or minus before, but have you ever seen minus or plus before? There is a small difference between them. So this identity can work with both a plus or a minus here, but if it's a plus here, then we need the minus over here. So the fact that this is plus minus and this one's minus plus tells you that, yeah, you can do whatever sign you want there, but you need the opposite sign over here. So if you're doing the cosine of an angle plus an angle, then you need the opposite over there. You see how these two are the same? So they're both plus or minus. In this case, you want to use the same side for both sides of the identity. And then tangent just has to go get all super complicated and throw a fraction in there. And one of the signs is going to be the same as the left in the numerator, but in the denominator, you're going to use the opposite side, opposite sign rather. So we're going to introduce and use these identities today. For a lot of this, we're going to need to evaluate trig functions at various angles, sine, cosine, and tangent. That's a good segue for our next bonus memorization quiz is coming up on Friday. Anybody been practicing for that? What's the cosine of 60? You know the cosine of 60? It's a half, yeah. What's the sine of 45? Root 2 over 2. Good. What's the sine of 60? Root 3 over 2. What's the tangent of 60? So that's what's going to be on it. It's only going to be from 0 to 90. Everything will be in degrees, but you'll have sine, cosines, and tangents. We're going to be evaluating a lot of stuff, a lot of sines, cosines, and tangents. Now, when we get to the actual test and you have to do these types of problems, you don't have to have it memorized. It certainly makes it faster if you do. But all the information is here on your unit circle. You do have to do a little bit of work to know what it is. So I want to practice using this unit circle. Can you guys flip yours over so you've got yours in front of you? And I'm going to give you some questions, and I want you to tell me what the answer is, okay? So can someone help start by refreshing us on, when we've got these two values in parentheses with the comma in between, what are we looking at here? They're coordinates of a point, but those are related to cosine and sines. Which one's the cosine, which one's the sine? X value is cosine, the Y value is sine. If you ever get confused about that, just go alphabetical order. C comes before S, X comes before Y. All right, so if I asked you for the cosine of 30 degrees, what is the cosine of 30 degrees? So find 30 degrees, look for the X coordinate. The cosine of 30 degrees is root 3 over 2. Okay with that? So could you guys please, and don't shout out answers, maybe just write them down in the margin of your paper. Can you find me the sine of 225 degrees? The sine of 225 degrees. Point to it on your paper. 225 degrees, and the sine is, are you pointing at negative root 2 over 2? Oh, you're so good. What is the cosine of negative 60 degrees? Cosine of negative 60 degrees. Remember, you need to be starting here and going in the negative direction, 60 degrees. Point to that on your paper. Cosine of negative 60, negative 60. So negative 60 would be here at 300, right? Cosine would be 1/2. Okay. Now, tangents get a little bit tricky because tangent's not on here, but it's okay because notice how all of these are over 2. The X and the Y's are over 2 inside the quadrants. And you know tangent is equal to what over what? Sine over cosine, right? So you can just take the value and the y value and divide it by the x value and ignore the over 2 parts. The over 2 part would kind of cancel out. Okay, so for example, if I ask you for the tangent of 60, that's sine over cosine, that would be √3 over 1, or just √3, and I can ignore the over 2 part. Okay, if I asked you for the tangent of 135, that's √2 over negative √2. Those are going to cancel out. It's going to be -1. All right, now the only tricky one is when you end up with 1 over √3. So if I ask you for the tangent of 30, you're going to end up with 1 over √3, and we're not going to express our answer that way. We're going to rationalize it. So 1 over √3 turns into √3 over 3. Okay, so we're going to be using those a bunch, so keep that handy. Let's go ahead and do some problems here then. So what sine or sum and difference formulas allow us to do is get exact answers for some other angles that are not on that unit circle. So we're going to start by finding the exact value of the cosine of 105 degrees. So we've got exact values for things like 90 degrees and 120 degrees, but we don't have an exact value for 105 degrees. It'd be around here someplace. So how are we going to do this? Well, 105 is a nice angle because it can be written as two of what I will call our familiar angles. The familiar angles are the ones that are on your sheet. What two angles on this sheet in degrees would add up to 105? 45 and 60 would work, right? So if we get an unfamiliar angle, we're going to try and think of a way that we can either add or subtract to get the same angle using the familiar angles. And we could do this one with 45 and 60. It doesn't matter which one we put it where. All right, so cosine, we need to use the cosine. Remember, I'm going to scroll up here. The cosine version, first thing I remember with the cosine version is you've got cosine, cosine, sine, sine. So they're grouped together. And I remember with cosine that the plus minus is opposite. So since we've got a plus here, I'm now going to have the opposite sign in here. And cosine is the one where the cosine cosines go together and the sine sines go together. And I like to actually build the format of it first, and then I'll go back and put the numbers in later. All right, so one of our angles is 45. This is why I'm color coding. I guess this isn't super important that you color code it. And the other angle is 60. Why is that helpful? Well, because we can evaluate this. We know, or we have access to the cosine of 45. It's on your sheet. What is the cosine of 45? √2 over 2. And cosine of 60 was a half. And the sine of 45 was also √2 over 2. And the sine of 60 is √3 over 2. And then we just simplify that as much as we can, and we're done. So final answer for me would be √2 over 4 minus, what's that going to end up being, √6 over 4. And that's it. Great things about these are that you can check them. So if you've got your calculator with you, go ahead and get that out. Double check, make sure you're in degree mode. We're doing a problem in degrees here. My goal is to evaluate the cosine of 105. So go ahead and punch cosine 105 into your calculator. Just checking my mode. I'm in degree mode. Get an answer. Is yours already going straight to the other version?
It went, yeah,
To this?
negative root 6 plus, yeah.
Interesting. You've got that fancy one. Then I'm going to type in what I think the answer is, and hopefully I'll get the same decimal. Do you know how to turn that into a decimal? Should you need to? Okay. Just make sure to close your parentheses with your radicals. So you'll see these problems on your test, and these ones are nice ones because you can check and make sure they're correct. Bless you. Okay, so your calculator does it. I'm going to need you to show me your work getting it by hand using the. So when I put a problem like this on the test, it will say use sum and difference identities to get an exact value. All right, any questions on that first one? Yes, thank you. This is an exact answer means it's not rounded. So if you did a decimal, you'd have to round it at some point. Even if you wrote all of these decimals, the calculator is rounding it off. So I would want it in this form. And simplify it as much as possible. Some people would prefer to write this as root 2 minus root 6 all over 4, write it as one fraction, that's fine. I've seen sometimes the book will do like 1 over 4 times root 2 minus root 6. I don't know why they do it that way, but that's fine too. Like it's the same thing, it's simplified. You know, go one step further than this, multiply it out and simplify it. Now there are going to be some that we'll have to rationalize that get kind of messy, but we'll do an example of that in a minute. Great question, thank you for that. Okay, let's do another one. Let's do one with radians. Yeah. Let's do the sine of pi over 12. Pi over 12 is not a familiar angle. I don't see it on my unit circle sheet. We got pi over 6, but we got no pi over 12. So I start thinking to myself, how can I make pi over 12 out of the angles that we do have? There's a couple ways to do this. That's 1 pi over 12, right? So I like to think of, I'm going to try and make two things. I'm going to make them both over 12. They're both going to have pi's over 12, but I need to add or subtract to get 1 pi over 12. Give me some numbers that would add or subtract to 1. For example, I could go 6 pi over 12 and 5 pi over 12. Couldn't I? Don't write this down though. 6 pi over 12 minus 5 pi over 12 is the same as 1 pi over 12. Agreed? Do you have 6 pi over 12 on your sheet? Reduce it. What is 6 pi over 12? That's pi over 2. Do you have pi over 2 on your sheet? You sure do. Do you have 5 pi over 12 on your sheet? No, so this is not a good way to do it. So if someone come up with another way that I could do this. Say again. 8 and 9. So if I did 9 pi over 12 minus 8 pi over 12, would that work? What is 9 pi over 12? That's 3 pi over 4, isn't it? 9 over 12 is 3/4. I'm just reducing fractions here, guys. I'm seeing some people giving me some bewildered looks. I'm just reducing fractions, okay? 9 pi over 12 is just 3 pi over 4, isn't it? And this would be 8 over 12 is 2/3. I could do that, yeah. It's got some 3/4 and 2/3. There's an even easier way to do it. That would totally work. In fact, can you try it that way and see what you get? I'm curious if it comes out looking different. How about 4 and 3? 4 pi over 12 and 3 pi over 12. That works, doesn't it? That subtracts to 1 pi over 12. What is 4 pi over 12? That's pi over 3, yeah. And 3 pi over 12? It's pi over 4. Yeah, those are both on there. All right, my students see this and they're like, oh, how am I ever going to figure out what blah, blah, blah. And I'd love for you to be comfortable enough with radians and fractions that you can do what we just did. However, there is an easier way to do this. If that's bugging you too much, we'll just convert to degrees. What is pi over 12? How many degrees is it? It's half of pi over 6, isn't it? So that's 15 degrees. 15 degrees, and then you can make 15 degrees out of what two familiar angles? 45 and 30 would be pretty easy, wouldn't it? Which is what pi over 3 and pi over 4 are, isn't it? Or no, it's not. No, this is 60 and 45. I could have gone 3 and 2. Huh, didn't think of that. All right, well, either way, however you want to do it, in degrees or radians, I'm sticking with radians. This is a sine and we're subtracting, right? So we need to remind ourselves with sine, that's the one that's got sine, cosine, cosine, sine. And do we go with the same sign in between or opposite? This has got a minus. So should we have a minus here in between these two things or plus? Same thing, right? Minus. And our two angles, or you choose whether you want to do radians or degrees. I'm doing radians because I can always get a little bit more comfortable with radians. So I got it all set up. All I got to do is evaluate. You're going to end up with some stuff that you're going to multiply and then subtract and then write down your answer. So I got sine of pi over 3 is root 3 over 2, root 2 over 2. Cosine pi over 3 is a half. That's root 2 over 2. Oh, didn't you get the same thing the way you did it? Ooh, are you sure it's minus root 6 over 4? Okay. Because one of your angles is bigger than 90, right? So the cosine would have been negative. Okay. So we got the same thing. And of course we could check, could type it in the calculator. How you guys feeling so far? Who's going to deal with radians, at least in the homework? Who's going to do degrees, no matter what? And the rest of you guys just aren't going to do it? Okay. Or you're undecided. Try the radians, try and deal with the radians as much as you can. It's going to make your life easier next year if you can get yourself more confident and comfortable with radians. However, I'd be honest with you, if I were working on the test, I would probably just go ahead and convert to degrees for these problems, especially the ones where you're just not like, I don't know what pi over 12 is. It's easier for me to think of an unfamiliar angle in terms of degrees. All right, we'll do one more here. You want radians or degrees? Let's just do degrees so we can focus on the mess that's going to happen because there's going to be a mess. Yep, we got to throw a good messy one in here. Did I say one more? I didn't mean one more. We got like 4 more. One more of these and then 3 more of the kind of simpler version problems. Tan 75. I bet you can find me a couple familiar angles that'll either add up or subtract to 75. 30 and 45 sounds good to me. So 30, I'm going 30 for my first one, 45 for my second one. All right, I'm trying to do this from memory. Tangent's the one that's got the fraction. On the top, it's tan, with either a plus or a minus in between. And I remember on the top it's the same, and the bottom it's opposite. So since that was a plus, this will be a plus. And then the bottom has a 1, and then a plus or minus, and then a tan multiplied. And the bottom's opposite, so this is going to be a minus. So I always set it up first and then come back and fill in my angles afterwards. 30, 45, 30, 45. All right, let's evaluate. Tangent of 30 is √3/3. And the tangent of 45 is 1. Hey, nice. And we got a 1 here minus, all right, tangent of 30, well, it's still √3/3. And tangent 45 is 1. We got problems here. Sine over cosine. So when I'm looking at 30 degrees, I know tangent sine over cosine. Sine is the y, cosine is the x. So when I look at this, when I do tangent of 30, I go 1 over √3, and then I rationalize it in my head. 1 over √3. Because they're both over 2, so I can ignore the over 2 part. So if I were doing it technically, it would be 1/2 over √3/2, but they're both, I could multiply that by 2 over 2, get rid of the, yeah. So just ignore the over 2 part. Just look at your numerators, 1 over √3, which is √3/3. Does that help? Awesome, thank you for that. All right, multiple problems here. We cannot have fractions inside of fractions. We're also not allowed to have radicals in the denominator. So we got to go through and fix this thing. I would start by getting rid of my denominators. So I'm going to multiply this whole thing by a fancy version of 1. Anybody want to guess what my fancy version of 1 is going to be?
Oh, the conjugate.
Not just yet. Let's get rid of the fractions first. I'll multiply by 3/3. Do you see why? What's this 3 going to do to the √3/3? It's going to cancel that 3 on the bottom, right? This is just going to become √3. This will become 3 because they both get multiplied by the 3, right? So that ends up canceling the 3 on the bottom. We just have √3 plus 1 times 3 is 3. The bottom we have 3 times 1 is 3 minus, and then 3 times this big old mess is just going to cancel the 3 on the bottom, get us a √3. That gets us to there. So we got rid of our fractions, our compound fractions, complex fraction, compound fractions. But we still have radicals in the denominator, which we can't have. And the way we get rid of those is the conjugate. So I'm going to multiply by another fancy version of 1. And it's going to be the conjugate of my denominator. So instead of 3 minus √3, it'll be 3 plus √3. Which, funny, that's exactly what was already on the top, wasn't it? So if you know your shortcuts for squaring binomials and multiplying binomial conjugates, then this should be pretty easy for you.
That's 3 and √3 in the right fraction. So it'd be 3. So the bottom would be 3 plus √3, and the top would be √3 plus 3, and then it'd be 3 plus 2.
Yeah, if that helps you see it, it's the same thing. It's still 1, right? And that helps you see that you are squaring 3 plus, or √3 plus 3. Do y'all remember the shortcuts for this? I'll go over it quickly. This is the a plus b, a minus b, right? Which is going to be a squared minus b squared. So a squared would be 9 minus b squared would be 3. On the top, we've got a plus b times a plus b, which is a squared, so which would be 3, plus 2ab, so 2 times 3 times √3, So 6 root 3 plus b squared, which is 9. AKA 12 plus 6 root 3 over 6, AKA 2 plus root 3. So these ones are the nastiest ones just because you gotta do some messiness. Let's double check and make sure I didn't mess up any of that. There's a lot of steps. Tan 75. So that, and I think that that is the same as 2 plus root 3. Hey, nice. All right, so these ones will get a little bit messy. If you've got fractions inside of fractions, go ahead and multiply by a couple fancy versions of 1 till you've fixed your answer. All right. Ready for the easy ones? Well, not easy, but easier. Yeah, you guys will like these. Okay, so this is kind of going backwards. You're going to see a block of problems in your homework that are going to be like this. So the problem would say the sine of 42 times the cosine of 11 minus the cosine of 42 times the sine of 11 equals, and they want you to simplify it. But in reverse, yeah. So you need to look at that and say, ooh, sine cosine minus cosine sine. Is that going to be sine of 2 angles being added or subtracted, or cosine of 2 angles being added or subtracted? Let me look at my cheat sheet here. Sine cosine minus cosine sine. That looks a lot like, ooh, it's definitely one of these two, isn't it? Does it look more like the one on the left or one on the right? The one with the plus or the one with a minus? Ours has a minus, right? So we could just rewrite this whole thing as the sine of those 2 angles being subtracted from each other. All right, this, I don't know if I can show the whole thing here. Where'd it go? This right here looks a lot like what we've got here, right? We got sine cosine minus cosine sine. And that is equal to sine of those 2 angles being subtracted. So I'm just going to write this as the sine of 42 minus 11. And then go one more step and say that's the sine of 31. And that's where you'd stop. That's it. That's it. So the instructions will say something like write it as an expression using only a single sine, cosine, or tangent or something like that. Basically simplify it. So like if they gave you, we'll do one more of these. Cosine pi over 5, cosine pi over 4, plus sine pi over 5, sine pi over 4. So if you've got your sheet with you, look for your sum difference formulas. You got 6 of them there. Which of those 6 most closely resembles the format of the expression you're looking at there? So look more like a cosine or a sine. Looks like a cosine because it's got the cosines together and the sines together. And if it's a plus here, then our cosine is going to have a minus inside, right? And the 2 angles are pi over 5 minus pi over 4. And yeah, we are going to subtract those things and practice our common denominator stuff. Good, that would be a good common denominator, 20. Yeah, let's do them over 20. So 1/5 would be what over 20? Would be, wouldn't that be 4 over 20? And then 1/4 would be 5/20. That makes this the cosine of, ooh, it's going to be negative pi/20. I bet the book will go one more step. Think about your, what do we call them? Odd even. When we have a negative inside of a cosine, what can we do with it? Do we bring it out or we just drop it? Sine and tangent, we bring them out. Cosine, it just goes away. So I imagine the book would probably give cosine of pi/20 as their final. I don't know, maybe not though. I would accept both of those on a test or a quiz, as long as it's a single sine or cosine. And if you had written it as like 2 pi/40, I might take off a 1/2 point for not reducing your fraction or something. All right, that's it. I need to check some of your homework, but I'll give you the homework assignment. It is page 468, 1 to 29 odd. And you got the rest, yeah. We got a pretty good chunk of time today, don't we? Hooray! Look at that. You might walk on without any homework today.
Very nice.